Okay, so section 4.5. This is a summary of curve sketching. So in sections 4.5 and 4.6, we kind of dig a little bit deeper, and I know this is weird to say because we've graphed a lot, but in sections 4.5 and 4.6, we dig a little bit deeper into sketching curves. Okay. Now I will say this for the next quiz, section 4.5, 4.6 quiz. I am going to allow you to use the red calculators. Okay, because section 4.5 is all about curve sketching by hand. Okay, curve sketching by hand. And then section 4.6 is all about using I know this is weird, kind of like they're opposites, but really section 4.6 is all about using technology to dive even deeper into what the graph means and what are the implications of the graph of the derivatives. So section 4.5 is actually going to be all on your computer, or sorry, all on your red calculator. And then section 4.6 is going to be all on your computer. Like literally part of the quiz, I will have you get out your computer, show all of the graphs, and explain what each graph means based on its derivative and what it looks like in terms of how does the derivative relate to the original, how does the double derivative relate to the original. But you'll get to it at that point. So section 4.5, you'll only be using the red calculator. Section 4.6, you'll only be using your calculator. So it's kind of like opposite ends of the spectrum. So section 4.5, we're going to try not to use the graphing functions of our calculator, only to check our answer. That's it. Okay? Only to check our answer. Only to confirm what we know and confirm what we see. We have learned all of the calculus stuff there is to learn about sketching curves. Okay? What we're going to do today is kind of look back all the way to Algebra 1 and Algebra 2 in pre-calculus and kind of put everything that we know about how to graph in one section. That's why the homework to this section, there's not a lot of problems. But each problem has a lot of work to go along with it. Okay? Which are working there. All right. So now, it would be a very good idea that you write down these guidelines for sketching curves. Because in your homework, all it says is use the guidelines to sketch. So you're going to have to know each of these, not like memorize. On the test, I will tell you, and I will be very explicit on where I want to see each piece. But for your homework purposes, please write these down, because I'm going to refer back to these letters every time we do one of these problems. So this is basically giving yourself a checklist on how to graph each thing. Again, please write these down. This would be a very good idea to write these down. First thing is writing the domain. And I'm going to always use the letter A to denote where the domain is. Your B is intercepts. Okay, so let's talk about each one, though. So domain. It's often very useful to start by saying what is in the domain, what is not in the domain. Right? We've been doing that since Algebra 1, right? Talking about the domain of a function. What are the possible x values that I could even plug into this function? And a lot of times it's useful to think about the range as well. But for our purposes here, we're just going to stick with the domain. It's often useful to start by determining the domain of f. That is the set of x values for which f of x is defined. And kind of more importantly, when is it undefined? What can't I have? Part B, finding the intercepts. Again, something that we've been doing since Algebra 1. Find the intercepts of the graph. Sometimes it's very easy. What if it's a linear function? Oh, really easy. Set it equal to 0, solve for x. There's your x-intercept. Or sorry, there's your x-intercept, I guess I could say. It's also very important to find the y-intercept. We know what that looks like from polynomials, from rational functions, anything. We can find the y-intercept pretty easily. Basically, plug 0 in for x and see what happens. It's funny that they say this. I will not usually let you omit this step, but look, it says finding the x-intercept. Sometimes it's very difficult to find x-intercept, right? Very difficult. You can omit this step if the equation is difficult to solve. Oh, really? We're just going to take that liberty and say, this is too hard. I'm just going to omit that step. The ones that I give you, I think it's very important to find the X-Intercept. The book says you can omit it. I say no. Part C, symmetry. You started talking about symmetry back in pre-calculus. Symmetry over the x-axis, symmetry over the y-axis. Is it odd? Is it even? First thing, when is it even? If f of negative x is equal to f of x, right? If you plug in negative x and it comes back out as the original function, then you know that it is even. If f of negative x is equal to f of x for all x in the domain, that is the equation of the curve is unchanged when you take x and replace it with negative x. That means that it's symmetrical about the y-axis, right? If you plug in x or negative x and it comes out to be the same y value, then it's even. And the curve is symmetrical about the y-axis. This means that our work is kind of cut in half. If it's symmetrical about the y-axis and you know what it looks like on the right side, flip it over on the left side. That's the convenient piece about even symmetry. For example, the basic parabola, x squared, right? If you know the parent function, x squared, if you know what it looks like on the right side, you just need to flip it over on the left side. We use that every time we solve for a quadratic in Algebra 1. I pick 2 points on the left of the axis of symmetry, and I'll just flop it over and find the right side. Second thing here about symmetry, is if it's odd. If it's odd, remember f of negative x is equal to negative f of x. Basically, if you plug in a negative, you can bring it all the way out, and if it's the complete opposite of the function, then you know that it's odd. For example, x to the third. That's odd, because if you take negative x to the third, you can bring that negative all the way out front, make it negative x to the third, right? So that means that that's an odd function. Another one is just a plain old y is equal to x. If I take x and I plug in negative x, that negative can come all the way up front. So it's basically y is equal to parenthesis negative x. It's the same as y is equal to negative x. So therefore it's odd. Now what does that mean? That means that you can rotate it 180 degrees about the origin. Now that's not as easy to see as a reflection across the y-axis. Can it be still useful? Yes, of course it can be very useful. Not as useful as an even function, but it's still pretty useful. The last one here is when it's periodic. When it has cycles. Okay. If f of x plus p is equal to f of x, basically if I can take a number, a constant, p, they call it in this case, stand for period. If you can take a number p and have it add to x, and it doesn't change the function, right? Like if you take sine and you keep adding 2 pi to x, it's not going to change the y values, is it? Same thing with cosine, same thing with tangent. The period there is 2 pi because every cycle of 2 pi, the y value is going to repeat themselves. That's what it means it's periodic. Okay, sine x has a period of 2 pi. Y equals tangent x has a period of pi. If we know what the graph looks like on an interval of length p, if we can tell what the function looks like on a period, on one single cycle, then we can say, okay, repeat that cycle, and there's our whole function. Next thing here, asymptotes. We've got horizontal asymptotes and vertical asymptotes. We talk about this a lot when we talk about rational functions. You've got to identify any and all horizontal asymptotes and any and all vertical asymptotes. Remember way back from section 2.6 that now we know we can use that limit definition, that if the limit as x goes to infinity or negative infinity equals some number, that's the idea of a horizontal asymptote, right? It's basically going to level out on the left or right side, far left, far right side. And we also know about end behavior as well. If we can say f of x goes to infinity as x goes to infinity, or goes to negative infinity as x goes to negative infinity, whatever, up on the left side, down on the left side, up on the right side, down on the right side, whatever it may be. Okay. Another thing about vertical asymptotes, and I have to write this in here, using our limit definition, they give it as like several big statements, but honestly, this is the best thing that I can, this is a way to summarize it. The limit as x goes to some value a from the positive or negative, left or right side, of f of x is positive or negative infinity. Okay, that's when you have a vertical asymptote. Is if you take x and bring it to some number, it's going to dive down or dive up on either the left or right side, and it doesn't matter. Right? If it dives down on the left side, then it's going to be a vertical asymptote. Dives down on the right side, it's going to be a vertical asymptote. If it dives down on one side and up on the other, it's still a vertical asymptote. But basically, this is saying if you have some number a from the left or right side, and it's going to go to negative infinity or positive infinity, that is a vertical asymptote. And again, we've studied that. We did that in Algebra 2 and probably again in pre-calc. But that just shows you where the asymptotes are. Now, all of that on that whole page is stuff that you had begun to study in pre-calc and Algebra 2. What we have on this next slide, this is all the calculus stuff. Intervals of increase and decrease. We use the ID test. We use the increase-decrease test used with the first derivative. Right? We compute f prime of x, find the intervals on which f prime is positive, increasing, negative, decreasing, which will then inform our maximum and minimum values. We can tell whether we have maximum or minimum values by finding the critical numbers of f prime, where f prime of x is equal to 0, or when it does not exist, right? We use that first derivative test, that ID test. If f prime changes from positive to negative, then it's going increase to decrease. That's a maximum value. If it's going decrease to increase, that's a minimum value. You know, we studied that on this test. You guys did pretty well on that. Just watch out for times when it goes positive, positive, or negative, negative. Those are times where the critical point would not be a maximum or minimum value. And again, although it is usually preferable to use the first derivative test, you can always perform the second derivative test to kind of confirm your findings. Obviously, we're going to be talking about increasing. I'm going to ask for the intervals of increase and decrease. So you're kind of already performing the first derivative test. No use to do the second derivative test, but still, you can. Remember, if you're using the second derivative test and it comes out positive, that means it's concave up, minimum value. If you use your second derivative test and it comes out negative, concave down, maximum value. Which again leads us to our concavity, right? Concavity and points of inflection. Remember the critical points of the second derivative. That's where you might have inflection points, right? You find the zeros of f double prime, or where it does not exist, right? Compute f double prime and use a concavity test. The curve is concave upward, where f double prime is greater than 0, concave downward, where f double prime is less than 0. Inflection points occur where the direction of concavity changes. And again, you find basically the critical values of f double prime. And that'll tell you where the possible inflection points may occur. Possible, right? Possible. You got to then find, use your number line test, and then sketch the graph. Okay. So for every one of these problems, now it's not going to be every single one of the homework problems that make you graph. Okay. There are some of these that ask you to find slant asymptotes, and we'll talk about that a little bit later on this section. Okay. But for everyone where it asks you to graph, the directions are going to say this. Like, look at the directions on example 1. This is what it's going to say in the homework. Use the guidelines. Use the guidelines. Okay. What are the guidelines? Well, you hopefully just wrote them down. I'm going to refer back to them here in a second. So, shall we? Let's go for it. This is kind of like a summary. Like, this is a big moment here. This is a summary of everything from beginning of Algebra 1, you know? Like, what is a domain? This is like a big moment here. to sketch this curve. And again, all we are going to use, I mean, you can use your graphing calculators, but do not use any of the graphing functions because you will not have that on your quiz. You'll need to use these red guys here. These are calculators. And be prepared on the test. One day is going to be a red calc. One day is going to be a calculator. All right. So first things first, let's find the domain. I'm going to go through each one of these things. Let's find the domain. Find the domain. Okay. When looking at the domain of this, I do have to pay attention to the domain because the domain, is it all real numbers? No. The domain is not all real numbers. What can X, I'll use a fancy set builder notation. Set of all numbers X such that X cannot be what? What can't X be?
0.
Plus or minus 1. When the denominator equals 0. Right? So you say X squared minus 1 equals 0. So X, well, basically that. X squared cannot be 1. So X cannot be plus or minus 1, right? So plus or minus 1. If you want to use interval notation, go for it. It's easier to do it right like that sometimes. If you were using interval notation, it would look like this. Negative infinity to negative 1, 1 to, or sorry, negative 1 to 1. Oh, no semicolon there. And then 1 to infinity. Basically everything but negative 1 to positive 1. No brackets on any of those. Okay, so there's our domain. The second thing would be to see what the intercepts are. Okay, so let's look at the intercepts here. So let's find our y-intercept. Why not? Let's find our y-intercept. Let's see f of 0. So this would be 2 times 0 squared, 0 squared minus 1. So that's 0 over negative 1, so 0. So I know it's going to run through 0, 0. That's our y-intercept, and coincidentally enough, one of our x-intercepts as well. That's our y-intercept. Now, to find the x-intercept of a rational function, you want to set the numerator equal to 0, right? You want to set the numerator equal to 0. So 2x squared equals 0. Oh, so coincidentally enough, I get another 0, right? So leads us back to 0, 0. The y-intercept is the x-intercept in this case. Now, some of you might remember this. Okay, if it's x squared equals 0, does anybody know what's going to happen if it's x squared equals 0? What's the multiplicity at 0? 2. So what's that going to happen at 0? Is it going to go straight through? It's an even multiplicity. What's it going to do? It's going to bounce, right? It's going to bounce off of 0, 0, right? Do I know now? Is it going to go from the top or the bottom? I don't know yet, right? But we know based on this, the multiplicity is 2. So it's not going to go straight through. It's actually going to bounce off of. It's going to like tangent to 0, 0. Remember, odd multiplicity will bend through. Odd multiplicities will bend through. Even multiplicities will bounce off of. Single multiplicities will go straight through. All right, so that's part B there, the intercepts. Let's look for C. C says to find if there are any sort of symmetries. Now, to find if there's any sort of symmetry, I find f of negative x. Let's see what happens. There could be no symmetry at all, right? Now, would you expect to see a periodic symmetry in this one? No, because it's not trigonometric. So why would we even be looking for that? Usually those periodic symmetries only happen in trigonometric functions. All right, let's find f of negative x. Well, f of negative x, that's 2 times negative x squared over negative x squared minus 1. Okay, so that's 2x squared over x squared minus 1. What happened when we plugged in negative x? We got the original, which means it's even. Okay, we have said here that f of negative x is f of x. So that means it is even. So that means if we know the right side, we know the left side. Okay, part D says, find any asymptotes. Now, are asymptotes going to come into play here? Yes, big time, because this is a rational function. So let's take a look at our asymptotes. Let's do horizontal asymptotes first. Right, the original, I'm just going to rewrite it. 2x squared over x squared minus 1. That was our function here. Do you remember the rules about horizontal asymptotes? Top heavy, bottom heavy, or equal, right? If it's bottom heavy, it's at 0. If it's top heavy, there is none. If it's equal, then it's at the leading where the leading coefficients, the division of the leading coefficients. What does that mean? That means that if the degree on top is bigger than it is on bottom, if it's top heavy, if the degree on the top is bigger than it is on the bottom, there is no horizontal asymptote. If the degree on the bottom is bigger than it is on the top, then the horizontal asymptote is at the axis. It's at y equals 0. If the degrees are equal, like this one here, we take the leading coefficient and it's y is equal to 2 over 1, the leading coefficients, 2 divided by 1. That's where our horizontal asymptote would be. So where is the horizontal asymptote? It's at y equals 2. Okay, so now for a vertical asymptote. Now remember, horizontal asymptotes, you got to look at the degrees. The vertical asymptote's quite easy. You just set the denominator equal to 0. So you said x squared minus 1 equal to 0. We've already done that. You get x is equal to plus or minus 1. That means there are 2 vertical asymptotes at x equals 1 and x equals negative 1. So think about visually what that should look like. There should be a vertical line at negative 1 and a vertical line at positive 1 that they're not going to cross. And a horizontal line at y equals 2 that it's going to reach on the right. And what's fancy enough about it being even, that if I know that it's going to get there on the right and it's even, isn't it symmetrical on the left side as well? Because it's even. So we know that if it's going to reach that point on the far right side of 2, horizontal asymptote at 2, on the far left side, it's got to do that exact same thing because it is even. All right, let's take a look at E. E says to find, now all the calculus stuff, intervals of increase and decrease. So that means I got to do the derivative now. Got to find f prime of x. Quotient rule time. All right, f prime g. So 4x times x squared minus 1, that's f prime g. G prime f minus 2x times 2x squared. All divided by x squared minus 1 squared. My voice is so soothing when I put Alex to sleep. He's doing that thing where he's closing his eyes. He's concentrating so hard that he had to close his eyes. Like his brain was working so hard that he had to shut his eyes. Okay, let's distribute in. So that's 4x cubed minus 4x minus 4x cubed over x squared minus 1 squared. Sweet. Negative 4x over x squared minus 1 squared. That's f prime. Okay, critical points then are, and again, that's what we're doing here, right? Yeah, critical points. Let's find our critical points. Where the numerator equals 0, okay, so negative 4x equals 0, so x equals 0. So critical point at 0. And then where the denominator equals 0. X squared minus 1 squared equals 0. Why? Because we got to consider not only where the derivative is in zeros, but also where the derivative may not exist. All right, so I would square root 0. I get 0. So x squared minus 1 equals 0. So x is equal to plus or minus 1 again. Those are the critical values. Let's do the ID test. Find the intervals of increase and decrease. So we have -1, 0, and +1. Where does it go back into again? The derivative, right? Goes back into the derivative. So in this case, if I plug in -2, now -2, that's going to be a positive divided by a positive, right? Anything squared is going to get me a positive number. So a positive divided by positive is a positive. Same thing here. If I plug in -1/2, it's negative, right? Negative times a negative is a positive on top. Positive divided by a positive, because the denominator is always going to be positive, is another positive. Any number bigger than 0, okay, 0, plug in 0.5, whatever. Negative times a positive is a negative. Bottom is always positive. Negative over positive is a negative. Same thing here. Plug in 2. -8 over something positive. So it's negative. So you can simplify your ID test by just thinking about them straight as positives and negatives. You don't care about the value. You just see what it's going to turn out, positive and negative. So this is an interesting little number line here, because now this means that the intervals of increase and decrease, so it is increasing everywhere from -infinity until 0. And it is decreasing from 0 to infinity. What does that tell you about -1 and +1? Are they maximums or minimums? No. Which makes sense, because is -1 or +1 part of the domain? No. See, we have to always think about back to our original statement about the domain being, oh, I can't have +1 or -1. So therefore, I could have thrown these out right away. They can't be maximums or minimums. Why? Because they're not part of our original domain. All right, so I've got my intervals of increase and decrease, and part F says, okay, then identify where my maximums and minimums actually are. Okay, I've only got one. It's at 0, 0, right? Is that a maximum or minimum? Increase to decrease. Maximum. Okay, I've got to do concavity now. Now, for concavity, I've got to find f double prime, which means I have to go and find the derivative of that, right? That's f prime. Got to do f double prime. Quotient rule again. Got excited about that. F prime, -4 times g, x squared minus 1 squared. Ooh, yikes, gross. Minus g prime. Ooh, this is going to be fun. Because when I do g prime, what do I have to do? Chain rule. The chain rule was an answer to an academic challenge question in the tournament, just saying. It said, what rule would you have to follow to find the derivative of a composite function? The chain rule.
Did you guys get it?
I don't know, actually. I'll have to ask her. I wasn't in that match. Okay, so chain rule it. 2x squared minus 1, right? That's the derivative of the 2 on the outside. So peel away the layer of the 2. Now we take the derivative of the inside. Derivative of the inside is 2x. Times, see that's g prime, times f. All divided by x squared minus 1 squared squared. Gross. Yes.
When it says 2 and then parentheses x squared, should that be squared again?
No, because that's just the derivative of the 2. So I bring the 2 out front and knock it down to 1.
Oh, got it.
Does that make sense?
Yeah. Chain rule rigs, come on. Girl, I was trying to figure
Chain
out.
rule rigs. Chain rule. Now, I'm going to do a little bit of simplification here. Negative 4 x squared minus 1 squared. I'm going to bring all of this. Okay, we got 2 times 2 times negative 4. So, actually, negative times negative, that's positive. And then we got 2 times 2 times 4, that's 16. And I'm going to leave this x squared minus 1, and you'll see why here in a second. Because down below here, I've got x squared minus 1. What's my power? Power to a power means we multiply to the fourth. I might not get to grab this. I only got 5 minutes left. I shouldn't have dilly-dallied. Now, what do you notice about every single term of this? What does it include? The x squared minus 1. So what I'm going to do is say, so long, farewell, reduce you. Okay. Each term had an x squared minus 1 in it, right? So I'm just going to reduce it by a factor of x squared minus 1. So this is a negative 4 x squared minus 1 plus 16 over x squared minus 1 to the third. Okay, now let's distribute in the negative 4. Negative 4x squared plus 4 plus 16 all over this thing to the third, which will reduce to negative 4x squared plus 20 over x squared minus 1 to the third. Oh, wait. I have something different. Where did I go?
I think you took away the x. Should it still be 16x?
Oh, look what I did. Oh, stupid Mr. Laverick. I let those go bye-bye. Those can't go bye-bye. That has to be an x squared in there.
Perfect.
Oh, jeez. Okay. Hold, please. So negative 4 and 16 make 12. Oh, jeez. Oh, Pete's. Sorry, that should be a 12x squared plus 4. There we go. 12x squared plus 4. All that to find where the possible inflection points would occur.
That's too much. It's necessary.
So let's find where the critical points would occur. Why does it keep doing that? I'm really mad at my board when it does that. So we say 12x squared plus 4 equals 0. But watch here. 12x squared is equal to negative 4. X squared is equal to negative 4 twelfths. When I go to square root that, what's going to happen? Non-real. So that does not exist. Nothing there. But you also must consider where the denominator equals 0. X squared minus 1 to the third equals 0. Cube root of 0 is 0. So look at this. Plus or minus 1 again. But wait. But wait. But wait. Can we have plus or minus 1? Is plus or minus 1 in our domain?
No.
Are there any inflection points? No. So this is not in the domain. So no inflections. Now, could we still run the concavity test to see what's going on? Of course. And I'm going to still do that. Spoiler alert. This would be positive, negative, positive when we plug it back into the double derivative. This guy here. 12x squared plus 4 over x squared minus 1 cubed. So that means it's concave down, or excuse me, concave up from negative infinity to negative 1. And then again at 1 to infinity. And concave down from negative infinity to, negative 1 to positive 1. I'm going to graph that tomorrow. We will finish this problem. That problem took like a half hour and stuff.
So I won't be doing the whole one.
I will say this. The nice thing about having these late start days and the rally days, the nice thing about having this class 4 period,
It doesn't.
this never gets shortened. This class never gets shortened for any reason. Yeah.
As
So
long as third period gets shortened.
we don't have to worry about that too much.
Are we doing notes tomorrow?
Yeah, tomorrow basically we're just going to do another problem, and then Wednesday is our work day. Yeah.
That's a long one.
Yeah.
But at least it's like everything that